Hi guys, and welcome to another Week 2 lecture video. I am Dr. Elizabeth Kyriakou, your lecturer for the semester, and today we're going to take a look at some problems on equilibrium. So we've already looked at equilibrium and our equations for equilibrium and our reaction forces. So now let's just take a look at the two types of questions we have for equilibrium. So equilibrium problems, we're going to have questions that are what we call particle equilibrium or rigid body. So when we talk about particle equilibrium, it is all the forces acting on one point. So they're actually simpler problems. And if we take a look at the question in your tutorial book, and I believe this is question 3.6, and we want to draw the free body diagram at A. So we're going to draw a free body diagram at point A. So what is it going to look like? Here we have a mass times an acceleration, so mg. So m is the mass, and g is gravity, and we usually take it as 9.8 meters per second squared. And we have a force in the horizontal, and here we have a cable. So therefore we're going to have tension in the cable. Let's draw our free body diagram. So here is our point A, and we have drawn axes, and we have our force mg going down from the crate. So we can call that Fa equals mg. So the mass of the crate, again times our gravitational force. We have a force at FAB, and we also have another force in the cable of FAC, and we have an angle theta here. So this is let me just draw some axes, X and Y. So this is our free body diagram. So now, whatever the question asks us, we can actually solve. So this question actually says, a 500 Newton crate is hoisted using ropes AB, so AB and AC. Each rope can withstand a maximum tension of 2,500 before it breaks. Rope A always remains horizontal. Draw the free body diagram for that ring A, which we've done, and determine the smallest angle theta to which the crane can be hoisted. Okay, so they've told us that this value is 2,500, so we can say FAC equals 2,500 newtons. And what are we going to do? And we need to find, what are we going to do with this force? We need to find theta. So I need to break this up into my horizontal and vertical components. So here I'm going to have FAC cos theta, and here I'm going to have FAC sin theta. So I can write out my equations for equilibrium. Sum of the forces in the x direction has to equal 0. Sum of the forces in the y direction has to equal 0. And sum of our moments around a point has to equal 0. Okay. So we know that this is also 500 newtons. They told us in the question, FA. So if I summate all my forces in the x and all my forces in the y, I should be able to find some of my unknowns. So if I say that sum of the forces in the x direction has to equal 0, so what do I have in the x direction? I have FAB minus FAC cos theta, and in the y I have sum of the forces in the y. We have FA, it's negative, and positive FAC sine theta. Okay. So if we let FAC equal 2,500 newtons, what are we going to have? We can find theta. So we can say that we know what that is. That's 500 newtons. We know that is 2,500 newtons. So we can solve for theta. So 0 equals 500 minus plus 2,500 sine theta. And then theta is going to equal sine to the minus 1, 500 divided by 2,500. So therefore, theta is going to equal 11.5 degrees. So, if you draw a free body diagram, no matter what the question is asking you, you can always solve it. We can use our equations for equilibrium and draw a free body diagram and go from there. That's our answer. So the next question we're going to take a look at is actually another question on equilibrium, but on a rigid body. But this time we're going to take again a look at a question with a cable. Clean this whiteboard. Okay, so this is going to be, let's just change this question. Alright, so this is problem 3.17 from your book. And the question says, draw the free body diagram of the jib crane AB, which is pin connected at A and supported by member BC, and neglect the weight of the crane. So what do we have? At A, here, we have a pin joint. So what does that mean we're going to have? We're going to have a X component, just draw an axis, an X and Y. We're going to have an X component and a Y component, the reaction force at pin A. We have our force from the jib of 8 kilonewtons, and the last force we have is actually tension in the cable. So we need to calculate T. So what's the first thing we're going to do? So we're going to draw a free body diagram. So this is what the free free body diagram is going to look like. So I'm going to have the beam, and I will have a force here of 8 kilonewtons. At A, I will have AX and AY, so reaction force, and at this point B, I will have tension in the cable. And here we have a Pythagoras triangle of 5, 3, and 4. So that's almost my free body diagram done. We've got our axes, X and Y, and I just need to put some dimensions. So we've got dimensions here, and there's actually a height difference here of 0.4 meters. So it's not acting through the point A. So we have all our dimensions on there? I hope so. So what's the first thing that we're going to do with this tension? We need to break it up into X and Y components. So I'm going to have T in the vertical, I'm going to have T 3 on 5, and in the X I'm going to have T 4 on 5. Alright, so now I should be able to draw, I've got my free body diagram, I should be able to actually calculate T. So let's write out our equations of equilibrium. So for equilibrium to occur, we have the sum of the forces in the X direction has to equal 0, sum of the forces in the Y direction has to equal 0, and sum of the moments acting at a point has to equal 0. So, to find T, I'm actually going to take the sum of the moments around A, because I have 2 unknowns at A. So what are my unknowns? My unknowns are AX, AY, and T. So, let's take our moments around A. So we're going to have this 8 kilonewton force, and it's going to go around point A in the negative direction. We're going to have the tension in the cable in the X component, and it's going to go in the positive direction around A, because just remember that there is a distance between there and there. And then in the Y component, it's going to go in that direction. So that's positive, and that's positive. Right, let's solve this. So, sum of the moments around A has to equal 0. So I'm going to have, should I write, that's 3 meters, and that's 4 meters. So I'm going to write out 8 kilonewtons, and that's going negative. My perpendicular distance is 3. So minus 8 times 3. I'm going to have T plus T 3 on 5. My perpendicular distance is 7 meters plus, that's going positive, T 4 on 5. And my perpendicular distance is this distance here, so it's 0.4. Have I included everything? So if I calculate that out, I can actually solve for T. So T is going to equal 5.31 kilonewtons. That wasn't so bad. Now what we want to do is we want to find AX and AY. So we want to find the reaction force over here. So we can say that, so we've used this equation. So to find AX, which equation are we going to use? We're going to go do sum of the forces in the x direction has to equal 0. So then we have AX, let's assign that to be positive, minus T 4 on 5. So AX is going to equal T, which is 5.31 times 4 on 5. So AX should equal 4.25 kilonewtons, and it's positive. Okay, so now we've used this equation. What do we have left to find? AY. So to find AY, we can say sum of the forces in the y direction has to equal 0. So we're going to have AY minus 8 kilonewtons plus T 3 on 5. We know that T is 5.31. So AY is going to be 4.82 kilonewtons. So there we have it. So what are the steps that we did to do this? We drew, first of all, our free body diagram. We broke our tension table up into its x and y components, and then we took some of the moments around A to eliminate AX and AY. So then we could find what T is. And once we found T, we could actually go to our next equation of equilibrium and find AX by some of the forces in the x direction to be 0, and to find AY, some of the forces in the y direction to equal to 0.